The light curve is supposed to be smooth, a clean, shallow dip as an exoplanet slides in front of its star. A simple geometry lesson written in starlight, and then inside the dip something small breaks the symmetry. A tiny bump, a dot-like blemish in the story. It's subtle, almost easy to miss until you place the next transit beside it. And the dot is there again, not in the same place in the sky, not as a separate object you can point to, but in the same place in the data carved into the transit of TRAPPIST-1f, like a recurring scar. It kept returning across 10 transits, insisting on being counted, insisting on being explained. This is where the hunt for signs of life becomes something quieter and more difficult than a headline. Because the first question isn't, is there an atmosphere? The first question is, what are we actually seeing? A transit is just a measurement of light. The star dims when the exoplanet passes in front of it. That's the foundation. But the title's promise is the disturbance inside that foundation. A transit dot on TRAPPIST-1f kept returning Starspot crossings across 10 transits. The hook is not just that something happened once, it's that it happened again and again. Repeatability feels like relief. In science, things that repeat can often be trusted, but repeatability can also be a trap. A confounder can repeat too. A bias can return with perfect discipline if the cause is stable. So we slow down and ask the key question in plain language. Is this dot telling us something about TRAPPIST-1f? Or is it telling us something about the star? Because the star is not a perfect light bulb, it's a surface. Picture a planet crossing a disk that looks smooth from far away, but is actually textured dark spots, bright patches. Regions of stellar activity that change what normal starlight even means. If TRAPPIST-1f's shadow crosses one of those features, the transit dip can briefly deepen or shallow in a way that looks like a small, localized signature. That's the core of a star spot crossing, not a new object, but a different kind of starlight being blocked. And now the tension hardens into a true signal versus artifact problem. The dot that kept returning could be a clue about the star's surface contamination masquerading as planetary detail. Or it could be something tied to the exoplanet, a hint of time variability, an atmospheric effect, some other structure that rides along with the planet's silhouette. But before we let our minds move toward atmosphere, we have to face the first and most stubborn alternative. Star spots are not just a nuisance. They are a way the star can impersonate the planet. This matters because we want to use transits to read atmospheres. We want to use faint wavelength-dependent differences, spectroscopy, when available to infer what gases might be present. We want to build a retrieval, a disciplined inference from tiny variations to an atmosphere's possible makeup. But if the star's surface is uneven, the measurement we thought belonged to the exoplanet can be partially written by the star. And that's how a story about a small dot becomes a story about epistemology, about what we know, what we infer, what we can only speculate. A spot crossing can imprint a localized feature in a transit light curve when the planet traverses a darker or brighter region. That's not conjecture. It's a known physical effect. The shape of the dip can be altered from within. Repetition across many transits can arise if the star has persistent active regions, and the planet's transit chord, the stripe it cuts across the star, stays stable. 10 transits is not a miracle. It's a chance to see whether a pattern persists, and that persistence is why the stellar explanation is plausible before we invoke planetary causes. A dot that keeps returning doesn't automatically mean the exoplanet is changing. It can mean the star is reliably non-uniform in the same places the planet keeps sampling. But the story can't end there, Because there is another kind of repeating enemy in this work, the machine. Small features can be mimicked by instrument systematics, detector effects, thermal stability issues, subtle calibration drift, especially when you're pushing measurements down into the realm where a tiny bump can change the narrative. The dot might be astrophysics, it might be hardware, or it might be an interaction between the two, a star's complexity amplified by a pipeline's assumptions. This is why the title's credibility thread matters. Kept returning is not just drama. It's the beginning of a test. If something repeats, you can try to break it. You can ask whether it moves when the wavelength changes, whether it stays tied to the transit's internal timing, whether it appears only in certain conditions. You can try to distinguish signal from artifact planet from contamination. And under the quiet awe is the ominous part. These are the kinds of features that can tempt us into overreading. If misread as planetary, a recurring dot could be mistaken for atmospheric structure, or for time variability, or for something even more seductive, a step towards signs of life. But that step would be built on an assumption we have not yet earned. So we hold the excitement at arm's length. We let the mystery stay small. We keep the exoplanet centered, but we don't grant it the dot by default. We treat the dot as evidence, not meaning. The question remains suspended in the transit of TRAPPIST-1f. What is that returning mark actually attached to the planet, the star, or the instrument? To answer, we have to reveal the chain. Photons to corrections. Corrections to models. Models to conclusions. How we know what the dot is, and how we know when we don't. The screen fills with a thin, trembling line. At first glance, it's almost nothing. A record of brightness over time, starlight counted and stacked into a curve. Then the exoplanet arrives and the line dips. It's the same quiet geometry as before, but now we're looking closer than comfort allows. Because buried in that dip is the dot that kept returning. And if we're going to claim it means starspot crossings or anything at all, we have to walk through how we know, not the romance, the chain. A transit measurement starts as photons on a detector, not a planet, not an atmosphere, just light arriving in a stream and being turned into numbers. The work of exoplanet science is taking those numbers and asking what physical story can produce them without cheating. So we begin with the simplest expectation, a smooth transit, a model of an exoplanet crossing a uniform star. That model gives you the baseline shape and depth. It's the first draft of reality, useful but incomplete. Because stars are not uniform and instruments are not perfectly still. Here's the test that the title forces in us. The transit dot on TRAPPIST-1f kept returning starspot crossings across 10 transits. That's a hypothesis, not a conclusion. The hypothesis says the planet's shadow repeatedly crossed a non-uniform patch of starlight. And we can't accept that just because the pattern looks familiar. We have to see whether the data behave the way starspot crossings should. The first task is humility: separate what's in the sky from what's in the machine. Before any physical interpretation, the data are corrected for known instrumental behaviors, subtle detector effects, thermal changes, pointing variations, trends that can bend a line and imitate a signal. This is where instrument systematics live. And it's where false certainty is born if we aren't careful. A small repeating feature can be an astrophysical fingerprint, or a repeated way the instrument and pipeline respond to the same observing pattern. Signal versus artifact isn't philosophy here. It's an engineering constraint. So we look for consistency checks that don't rely on believing our favorite story. One of the most powerful checks is what stays and what changes when you change color. Because star spots don't just change brightness, they change the spectrum of the starlight itself. If you can observe in multiple wavelengths,
Look at the
if you can
repetition
compare
starting
how
at
the
40
transit
hertz.
looks in different
It's
bands,
synchronized with the external
Starspot
input.
and Facula
You need to
effects
isolate that frequency
often
now.
leave chromatic signatures. In plain terms, a spot's contrast can be stronger in some wavelengths than others, meaning its imprint inside the transit can scale with color. An atmosphere can also be wavelength dependent, but in a different way through absorption and scattering. That's the fork in the road where spectroscopy becomes
This anomaly
tempting.
keeps repeating at precise intervals.
It can be the bridge from
Let's
a
align
light
the
curve
comparison
to
model.
an atmosphere.
Yes, it locks right in.
Or it can be the
The
place where the
waveform is
star
stabilizing. See the repeating
impersonates
pattern?
one.
Yes,
So the
frequency
method
is
becomes a
unusually
set
high
of
for this
questions you can
dataset.
ask the
We
returning
need to isolate
dot.
that signal
Does the
immediately.
dot align at the same place within the transit each time tied to the planet's path across the star? If the bump repeats at consistent phase in the transit, that supports the idea that the exoplanet is sampling the same stripe of stellar surface again and again. It doesn't prove star spots, but it makes a stellar surface explanation plausible. Does the dot's shape and timing
There it is
behave
again,
like
right
a
at the apex.
localized crossing event
Overlaying the model now,
rather than random
it matches
noise?
the signature.
A spot crossing is not just any wiggle. It's a structured deviation embedded within the transit with a shape that can be modeled. If you can fit it with a spot crossing geometry and the fit is stable across transits, you've earned something. Not certainty, but traction. And then the hardest question, what's left after you do everything you can to remove the obvious alternatives? This is where how we know becomes less about fancy tools and more about disciplined skepticism. You take the raw light curve, you correct it, you fit a transit model. Then you look at the leftovers,
The activity spike
the
correlates here.
residuals,
Yes, but the
and
transit
you ask, do
depth
the
changed
residuals
after
look
the
like
layer
random
update.
scatter, or
Zoom
do
in
they
on that
hold a
anomaly.
repeating fingerprint? When the dot kept returning across 10 transits, it offered a rare gift. Repetition is a lever. You can press on it. You can also press on the pipeline itself. A rigorous approach includes redundancy, different plausible
If we adjust
corrections,
for the parallax, this
different
hypothesis
modeling
holds true.
choices,
Only if the
and
dark matter
checks for whether
calculation
the
is
dot
correct. We
survives
should check
those
the new data.
choices. If a feature vanishes when you change a reasonable calibration step, it may be calibration drift or an unaccounted detector behavior masquerading as astrophysics. If it survives across sensible reductions, it becomes harder to dismiss as pure instrument artifact. But even if the dot survives the machine, there's another layer where we can fool ourselves, the assumptions we build into our interpretation. This is where exoplanet retrieval can become both powerful and dangerous. Retrieval is the act of inferring physical parameters like atmospheric composition or cloud properties from data using models. But models aren't reality. They're controlled simplifications. And the moment you treat the star as uniform when it isn't, hey, you can push an atmospheric retrieval toward the wrong answer with total confidence. That's why the outline's warning matters here. Retrieval prior/model assumptions are not technical footnotes. They are decision points. One-dimensional versus
The
three-dimensional
Singapore cluster
atmospheres.
just went gold.
A single temperature
That's
profile.
a high priority alert. Patching it through
Equilibrium
to the main
chemistry. Even the assumption that the stellar surface is a clean backlight. Each choice can bias the output. In the case where a dot kept returning,
We need to
a
isolate the
disciplined
M-dwarf flare signature.
interpretation leans toward the most direct explanation.
Switching to the activity model
for
now.
stellar heterogeneity, sampled repeatedly by a stable transit cord. But we still keep a sliver of openness. A planet's atmosphere can also produce wavelength-dependent signatures. The danger is confusing wavelength-dependent with planetary.
Hypothesis A is straightforward,
Stellar
but look at the
contamination
deviation
can
here.
be
We have to test
wavelength-dependent
hypothesis
too.
B,
So
even
what
if
can
it
we
takes
honestly
longer.
say at
The
this
data
stage
supports it.
before we become hypnotized by the idea of atmosphere? We
Scene
can say the
985.
method exists to test the Starspot
Possible
hypothesis,
explanations.
multi-wavelength behavior, consistent transit phase, model fits that reflect localized crossing events. We can say the instrument must be interrogated so the dot isn't a repeating machine echo. And we can say that any atmospheric inference must be conditioned on a stellar surface model, not draped over it like an afterthought. And we can say the title's tension is real. When the dot kept returning across 10 transits, it didn't just offer a clue, it set a trap. The trap is to treat the exoplanet as the only actor when the star is half the stage. To escape it, we have to change what we think we're watching, because the next turn in the story is unsettling. The star isn't just the background. In this kind of measurement, the star becomes the instrument. The animation is simple at first. A dark circle glides across a bright disk, a transit clean and familiar. But then the disk begins to change. It's no longer a uniform coin of light. It's textured subtle modeling, darker islands, brighter seams. And suddenly you can feel the ground shifting under the measurement. Because the exoplanet isn't crossing a star, it's crossing a surface. This is the change of perspective the evidence demands. TRAPPIST-1f is still the exoplanet at the center of the frame, but the dot that kept returning forces our eyes to the star's skin. If the anomaly repeats across 10 transits, the first question becomes not what does this say about the planet's atmosphere, but what does the star do to our ability to read that atmosphere? This is where the search for signs of life grows both more precise and more precarious. We want to read atmospheres because atmospheres can carry biosignature patterns, chemistry that on Earth is tied to biology. But around a small active star, the same kinds of spectral hints can be distorted by contamination. Not because nature is trying to deceive us, because our measurement is indirect and the star is part of the signal. So we name the tension plainly planet atmosphere versus star contamination. Unocculted spots and faculae regions the planet does not cross can still bias the measured transit depth and can do it differently at different wavelengths. That means a transmission spectrum can inherit the star's patchiness. It can look flatter than it should. It can tilt. It can mimic or mute features we would otherwise associate with an exoplanet atmosphere. And now the returning dot becomes more than a curiosity. It becomes evidence that the star is not safely ignorable. A repeating in-transit feature suggests the planet is sampling a consistent band on the stellar surface, the same transit chord over and over. If that chord intersects a persistent active region, the imprint can return with unnerving reliability. The dot kept returning, not because the planet is whispering secrets, but because the star is holding still just long enough to fool us. The visual shifts to a narrow stripe drawn across the star's face, the path TRAPPIST-1f takes each time. It's a thin slice of reality, and what we learn from that slice can be exquisitely detailed if the slice is representative. But if the slice is unusual, if it's darker or brighter than average, then our inference about the planet is built on biased illumination. This is the quiet horror. At the heart of exoplanet atmosphere work, you can do everything right and still be wrong because the star is a textured light source. And the deeper you push toward biosignatures, the more this matters. Because biosignature grade claims live in small differences, tiny slopes, subtle absorption patterns, shapes that can be muted, smeared, or impersonated. So we bring in another confounder that often sits beside stellar contamination, like a shadow the planet's own ambiguity, clouds and hazes. A flat or muted spectrum can mean the exoplanet atmosphere is cloudy or hazy, hiding deeper molecular features. But a flat spectrum can also be what you get when stellar contamination washes out the contrast. Two different physical stories, one similar observational outcome. That's cloud/hazes degeneracy, and in this case, it's braided tightly with the star's heterogeneity. This is how the story tightens. The returning dot doesn't just complicate the measurement inside the transit. It casts doubt on interpretations outside the transit as well. It warns us that the star may be shaping the entire inference chain. And then there's time. 10 transits feels like a comforting number. It implies patience, repetition, statistical confidence, but time can betray you in two directions. Stars change. Active regions evolve. Patterns rotate in and out of view. Even if a feature seems stable, it can be slowly morphing. And the way you sample it, your cadence, your gaps, your limited window, can make change look like constancy, or constancy look like change. So we name the confounder the outline demands here, time variability versus sampling. If the dot appears to repeat, that might be because the star's active region is persistent. Or it might be because the observation cadence catches the star in similar states, creating an illusion of stability. 10 transits can reveal consistency, but it can also conceal evolution if the baseline and sampling don't capture the full behavior. This is not a reason to despair. It's a reason to be specific. The change of perspective is not the star ruins everything. It's the star must be modeled as part of the measurement. That's the adult version of awe we still reach for atmospheres and signs of life, but we do it with an accounting ledger for the star's influence. Stellar contamination is a first-order term in the uncertainty budget for M-dwarf exoplanet atmosphere interpretation. If you ignore it, you don't just add noise, you can shift the answer. And in the case of TRAPPIST-1f the dot, that kept returning acts like a warning label. It suggests the star's surface structure is not a minor detail. It's potentially central to what we think we know about the exoplanet's atmosphere. For a moment, we allow a brief calibration. In the mind, if Earth were backlit by a perfectly uniform sun, we might dream of reading its atmosphere cleanly. But our reality, even in our own system, is messy. Light, complex surfaces, and inference under constraint. And then we return immediately to the exoplanet case, because that's the only place we're allowed to stand. So what do we do with this perspective shift? We do what the scientific method demands. We attempt an honest synthesis. We don't chase the most exciting interpretation. We chase the interpretation that survives the hardest test against false positives. And that means we're approaching a threshold moment, a best current conclusion, not a final answer, a defensible one. Because when the dot kept returning across 10 transits, it wasn't just an invitation to imagine. It was a demand to decide what we can responsibly say and what we must leave unresolved until better constraints arrive. So we gather the competing stories, starspot crossings, instrument echoes, atmospheric temptation, and we prepare to weigh them limitation by limitation without flinching. The evidence board is quiet, no music of triumph, no single plot that settles everything. Just 3 columns in plain sight: starspot, instrument, atmosphere, and the uncomfortable discipline of deciding what deserves a check mark and what only earns a question mark. This is where the story has to be honest. Because the title promised a simple hook transit, dot on TRAPPIST-1f kept returning starspot crossings across 10 transits, and the hook is persuasive. Repetition makes us want to believe we're closing in on truth. But repetition can also be the most convincing form of bias. If the star is consistently patchy where the exoplanet crosses, the measurement will consistently carry that imprint. If the instrument repeats a behavior under similar conditions, the artifact will faithfully return. The dot can keep returning without belonging to the planet at all. So we ask the section's question without ornament, given 10 transits and a recurring anomaly. What can we responsibly conclude about TRAPPIST-1ef's atmosphere, if anything? First, what we do not do. We do not treat a small in-transit feature as a doorway to signs of life. Not here. Not with this confounder on the table. A biosignature claim without a stellar contamination model is not bold. It's fragile. Now what we can actually say. Spot crossing events are expected in transit photometry when stars have heterogeneous surfaces. This isn't an exotic explanation. It's a baseline reality for many active stars, especially when you're measuring at the precision needed for exoplanet atmosphere work. And in this case, the dot didn't appear once and vanish into noise. It kept returning across 10 transits. That matters. But it matters in a particular direction. Repetition. Across many transits, strongly supports a stable geometry, the planet's transit chord repeatedly sampling a persistent stellar surface feature. A star-spot crossing hypothesis fits the most conservative reading of it happened again. Not because it's the only possible story, but because it's the story that requires the fewest additional assumptions. So the board gets its first strong checkmark. Stellar contamination is not optional here. Now we test the other suspects, because most conservative is not the same as certain. Instrument systematics remain a live threat. A recurring feature can be manufactured by a consistent bias, but the key here is what survives correction and modeling. If the dot persists through reasonable calibrations and different reduction choices, it becomes harder to blame purely on instrument systematics. That doesn't absolve the machine. It narrows the suspicion. And then there is the most tempting column atmosphere. This is where we have to speak carefully, because atmosphere is both the reason we watch these transits and the easiest place to overreach. Any atmospheric interpretation must be conditioned on a stellar contamination model. Without it, molecular claims are fragile. Even if later observations provide wavelength-dependent structure that resembles absorption, the star can sculpt that structure. The data can be real and still misattributed. That is the central false positive risk in this niche, not made-up data, but misread data. This is the core of the best current conclusion. Limitation heavy by design. The dot that kept returning is best explained first as stellar surface structure intersecting the transit path. And until that stellar contribution is bounded, the exoplanet atmosphere cannot be cleanly read from the same signal. That's the conclusion. But it's not the end of the thinking. It's the beginning of a stricter kind of curiosity. Because what if after modeling the star, something still remains? What if there is a wavelength-dependent component that refuses to fit the stellar story? Here the outline allows only a careful doorway, and we take it with restraint. If future data isolate a wavelength-dependent component inconsistent with stellar models, it could reopen the atmosphere question, but that threshold is high. That's not a promise. It's a conditional. It's how honest science leaves room for the world to surprise us without pretending it already has. Now we rotate to the confounders that can quietly inflate confidence, even when the story feels coherent. One is the seduction of a good fit. A model that fits can still be wrong if the model's assumptions are wrong. That's not poetry. That's mathematics. So we name what could mislead us next, especially if spectroscopy enters later line misidentification / incomplete line lists and retrieval prior / model assumptions. If a later spectrum shows a feature that looks like a familiar molecule, the identification depends on line lists and on how the retrieval is constrained. If the retrieval assumes a uniform star or assumes a simplified atmosphere, it can produce an apparently precise answer that is precisely biased. This is why best current conclusion must be spoken in two voices at once, the voice of what's most likely and the voice of what could fool us. So what's most likely? The dot that kept returning across 10 transits points most strongly to star-spot crossings as the leading explanation, making stellar contamination central to interpreting TRAPPIST-1f's transit data. What could still fool us? Instrument echoes that survive naive calibration, time variability that masquerades as stability, and model assumptions that launder uncertainty into confidence. And what does that mean for signs of life? It means we are not at a biosignature moment. We are at a measurement integrity moment. The story is still profound because this is the cost of seeking life through faint starlight. You must first prove you can read the page without confusing the ink for the paper. The evidence board remains on screen, but the marks are honest. Starspot strong, instrument interrogate. Atmosphere not yet not from this alone. And now we turn toward the final kind of rigor the title demands. Because the dot kept returning is not just a clue about TRAPPIST-1f. It's a lesson about inference itself. When a signal repeats, does it mean truth or repeating bias? We're ready for the cosmic checkpoint, but it will not drift into galaxies or grand philosophy. It will stay anchored to this small returning mark and the measurable unknown it names. The 10 transits lay on top of each other like translucent pages, a ribbon of time. A narrow dip repeated each pass of TRAPPIST-1f across the star, leaving its signature in the light. And there, inside the dip, the same small disturbance appearing again, nearly in the same place, as if the data itself has learned a word and won't stop saying it. The dot kept returning. Across 10 transits, it returned with a steadiness that feels almost intimate, like a heartbeat. You can't locate in a body you cannot touch. But this is the cosmic checkpoint, and it has a single job to remind us that repetition is not the same as truth. Repetition can also mean repeating bias, especially when the star is not a clean backlight, and the measurement is a fragile subtraction performed at the edge of certainty. So we ask the final key question, as plainly as possible: what future observation would most cleanly separate TRAPPIST-1ef's atmosphere from the star's contamination? Because that is what this whole case has become. Not a mystery about a dot, a diagnosis about an inference chain. Transit-based atmosphere inference is fundamentally differential. It relies on tiny wavelength-dependent changes to suggest gases, clouds, or temperature structure in an exoplanet atmosphere. That's the promise at the heart of this niche. The idea that starlight filtered through a limb of atmosphere can carry chemical fingerprints. But the dot that kept returning warns us that the star is also imprinting fingerprints. In TRAPPIST-1f's case, a persistent recurring in-transit feature increases the odds that stellar surface structure is part of the measurement. This is not a disappointment. It's a constraint. It is the data telling us what the data is made of. Now we name the tension pair that sits at the center of this checkpoint detection versus interpretation. We can detect the dot. We can measure that it returns. But interpretation, what it means, depends on whether the dot is born in the planet, the star, or the instrument. And this is where the search for signs of life is most vulnerable, not to lack of imagination, but to overconfident attribution. So the checkpoint is not cosmic in scale, it's cosmic in discipline. We separate what we know from what we infer. We know transits can be measured, stacked, modeled. We know star spots and faculae exist as stellar activity features that can change transit shapes and apparent depths. We know instrument systematics can create small repeating structures if not controlled. These are not speculative problems. They are established realities of precision photometry and spectroscopy. We infer that for TRAPPIST-1f, the returning dot is more consistent with stellar contamination starspot crossings than with a planetary novelty. That inference is conservative, and that's why it's strong. And now we allow a careful statement about what would increase confidence. Confidence rises with independent constraints. On the star activity indicators coverage of spots and faculae chromatic behavior that reduce the degeneracy in retrieval. In other words, the more we can bound the star's heterogeneity, the more safely we can interpret what remains as atmosphere. This is where the story touches biosignatures without committing the sin of implying detection. Even if someday we seek biosignature patterns in TRAPPIST-1f's atmosphere, we will have to make the star legible first, because stellar contamination can masquerade as atmospheric slopes mute features or produce apparent structure that a retrieval might mistake for molecules. A biosignature claim must survive false positives, and stellar heterogeneity is one of the most persuasive false positives in this entire observational channel. Technosignatures too belong here only as a boundary line. If we ever looked for industrial gases or other technosignature-like atmospheric anomalies in exoplanet spectra, they would live in the same fragile inference space, and they would remain unless every confounder, especially contamination, had been constrained beyond reasonable doubt. The dot that kept returning is a warning about that entire class of hope. So what is the named unknown we can measure next? It isn't, is there life not yet? It's something more fundamental and more actionable. The named measurable unknown is stellar heterogeneity, the relationship between what TRAPPIST-1f's transit toward samples and what the rest of the stellar disk is doing unocculted spot and facula coverage in the same wavelengths used for atmospheric inference. That is the uncertainty that can be quantified, bounded, reduced. If we can measure the star's modeling, how patchy it is, how it changes, how its spectrum differs across regions, then we can subtract the star more honestly from the planet. And if we can do that across multiple wavelengths and repeated transits, we can test whether anything left behind behaves like an exoplanet atmosphere rather than like a stellar surface. That is the future data that resolves this case-coordinated multi-wavelength monitoring, repeated transits, and stellar activity tracking that turns contamination from a lurking unknown into a modeled term. Not a single heroic observation, but a patient narrowing of uncertainty. And this is what the dot returning again and again ultimately teaches. Sometimes the universe doesn't offer a clear message. It offers a repeating syllable. And our task is not to declare what it means, but to learn what could possibly be saying it. So we end where the title began, but with a different kind of awe. The dot kept returning, and in that persistence, it showed us the limits of interpretation and the path forward. In the end, the last question is measurable, not mystical. How modeled is the star in the exact light we use to read the planet?